We talk a lot about pressure, and I thought it would be kind of a neat exercise to go through what exactly is the point behind pressure. Why does it matter so much what the end diastolic pressure is? And that's what that ED means. And to do that, I think one of the best ways is to say, well, what happens if we change it? What would be the result of changing the pressure at the end of diastole? So the first change that you would see is, you remember there's that equation around preload equaling, we know, pressure at the end of diastole times radius at the end of diastole. And of course, then if pressure goes up, then preload would go up. And we know that wall thickness times 2 is in the denominator. So the first thing I would say is, well, if you say pressure goes up, or if that's our assumption, then we have to assume that preload would go up as well. So that's the next thing. Well, you might say, okay, well, let's take it a step further. So what? That preload goes up. How does that change anything? Well, again, I think it's helpful to kind of think about what preload is, and then some things will become very, very obvious right away. So if we look at a cut section of the left ventricle, this is my left ventricle, and I've kind of sliced through it, then you've got pressure kind of hanging out in here. This is our end diastolic pressure, the same thing we started with, right? Pressure at the end of diastole. And if you increase that pressure, then you're going to cause some changes around the walls, right? You're going to have wall stress, and we know that wall stress at the end of diastole we call preload. So basically these yellow arrows represent preload. And in fact, I might even point out to you that if I actually zoomed in, there would be a little red cell, like a little squarish, and that little red guy, that little red cell, let's draw him over here, he's actually going to start feeling, he's going to literally start feeling the effects of stretch. So he's hanging out nice and happy, and all of a sudden this little fella is going to get stretched. He's going to start looking like this, and I don't think he would be upset. I think he would look just as happy, but he might look like that. All stretched out, his eyes stretched away from his smile. So this is what our cell will begin to look like if we continue to stretch. And the reason is because you're literally yanking on the two sides, right? So that's what becomes of this process. This causes these cells to almost look like little pancakes. And I say pancakes just because I enjoy pancakes so much. But just remember that the cells flatten out and they stretch out, and that's a direct consequence of the increased preload. So this causes increase, I'm just going to write stretching. So, and in fact, maybe I should even say stretching of heart cells, just so we don't forget exactly what we're talking about. So stretching of heart cells, and you can literally imagine it, right? You can imagine these little cells getting stretched out. And you can also imagine, if you think for a moment, of all of the contents of the cells getting stretched out. So stretching actually stretches out not just the cell itself, but everything inside the cell. And a few interesting things begin to happen when all of the proteins inside of a cell get stretched out. So there are two important things that happen with stretching. And now we're getting into kind of the meat and potatoes of increased pressure, what it causes. So stretching itself is going to happen, and I think that part, you can kind of reason through that and kind of assume that, that makes sense. And one thing that it causes is what we call the Frank-Starling mechanism. So, obviously named after two folks named Frank and Starling. And the Frank-Starling mechanism, we'll actually get into some details about this separately. But the Frank-Starling mechanism is, put simply, it's going to be something like this. I'm going to draw out now the myosin and actin. So remember, myosin's got these fantastic little myosin heads always looking to work, right? They're always looking to bind actin, and they're on both sides, and so I'm going to just draw it here. So here in purple is just my myosin bit, and I'm going to actually cut and paste this and show you what it could look like on the side. So I'm going to draw kind of two versions, and we're going to start seeing how the Frank-Starling mechanism, very quickly, how it makes sense. So we've got this actin kind of sitting here, and it's on both sides, right? So it's going to be on both sides. In this first kind of drawing, I've drawn things very crowded, right? There's a lot of crowding happening there. And so you basically get these areas where, for example, let's draw it here, these two myosin heads and these two myosin heads are literally being blocked by this actin. So, for example, these two myosin heads are being blocked by that actin, and these two are being blocked by that actin, because they would both like to be on their other side, right? They would like to be on this binding to that actin, and this set would like to bind to that actin. So you've got actin crowding out other actin, right? Which sounds kind of funny because you think, well, so what? How come the myosin doesn't just simply bind the actin that's closest to it, right? That seems like an obvious solution. But in fact, actin has a polarity, right? So it can only really bind in one direction. So when things actually get crowded, that becomes a major problem, because now myosin literally can't get to the actin with the correct polarity, as you see in the first diagram. So what happens at the Frank-Starling mechanism is that when you stretch out your heart cell, you're also stretching out, as I said, all the proteins within, and now you've got a lot of happy myosin heads. These guys are happy, right? These guys are happy, and these guys are happy as well. So basically what you see is that by stretching things out, you can actually get more myosins back on the job. And so that's kind of the key with the Frank-Starling mechanism, is that you have more myosin heads at work. Myosin heads at work. So this is a key point. And there's some nuances to it. I've kind of simplified the Frank-Starling mechanism. There are some important nuances we'll get into, as I said, later. But this is one of the key elements of it. And the other stretching-related mechanism is called an inotropic mechanism. Inotropic. And usually when you think of inotropic, you're probably thinking that it has something to do with calcium. And you're right. Inotropic does have to do with calcium. And what it means is that basically, let me actually give a little bit more space. If we were to zoom in now, remember we have our actin and myosin, and you know how valuable it is to have the two binding to each other. If you have something like this, where your actin is there, and let's say you've got a myosin here, hoping to bind to it, this is our myosin, then what you see is that the actin is guarded. You remember it's guarded by what? It's guarded by tropomyosin, right? That's the protein that's kind of acting like a chaperone, right? Making sure that the myosin and the actin don't interact. So this is our tropomyosin. Again, you can think of it as a chaperone, right? Just protecting that actin. And the thing that's going to help us move the tropomyosin out of the way, the thing that's going to help us move it out of the way, is none other than our friend troponin. So this is our troponin, and troponin is going to scooch the tropomyosin away. And troponin comes in 3 protein bits, and we call them troponin C, troponin I, and troponin T. And it's the troponin C that I'm going to focus on for right now. So the troponin C, let's say, is looking like this, right? This is our troponin C. And remember, it's going to potentially bind to calcium. In fact, it will bind to calcium. This is my calcium, right? So this is my troponin C and my calcium. When things are stretched out, so when things get stretchy, I'm going to say stretched, well, the proteins feel that. And the troponin C is going to look stretched. It's going to look like that. So this is my troponin C, right? All stretched out. And troponin C, the stretched out version, literally behaves slightly different than the troponin C when it's not stretched out. So troponin C, when it's not stretched out, is thinking to itself, well, maybe I can bind calcium, maybe not, you know, I'm not particularly plussed either way. So it's thinking, maybe I don't want to bind calcium, maybe I do. But the troponin C that's stretched out is saying, yes, please, let's bind. So it's screaming to bind with calcium. So that's a big change, isn't it? Because if troponin C wants to bind calcium, and that's exactly what happens when things get stretched out, is that troponin C kind of changes its shape, and now it really wants to bind calcium. If that happens, then all of a sudden the troponin C is going to be more effective at getting tropomyosin out of the way, and myosin can now bind actin. So let's recap these two mechanisms. They have a lot to do with each other, right? So when things stretch out, the Frank-Starling mechanism allows more myosin heads to get to work, and the inotropic mechanism basically is kind of a change in the way that troponin C's shape is, and that change in shape makes it want to bind calcium very eagerly. So let's put it together. You've got more myosin heads at work. That's what Frank-Starling taught us. And as far as the inotropic mechanism, you may not have more calcium, but what calcium you do have is going to have a bigger effect, right? Because the troponin C really wants to bind to it. So calcium has a bigger effect. So if you think about them, you've got more myosin now, and the calcium is obviously going to help the myosin bind to actin more easily. So putting it all together, you're going to basically get more myosin burning up ATP and turning it into mechanical force, right, or mechanical energy. So the end result of all this is that you have a larger mechanical force, larger, I'll say, left ventricular force of contraction. So this is kind of the end of the day what you're going to get. And as you get that larger force of contraction, I could go even further and say, well, what is that force? Well, it's pushing against blood, and that's pushing out on a certain area, and force over area is pressure. So a larger force of contraction really translates into what you're saying is a larger left ventricular pressure. Larger left ventricular pressure. And this, just to be very, very clear, is going to be during systole. So we started talking about diastole, right? The question was, well, you know, what the heck is the point of, you know, knowing about preload and end diastolic pressure? And the point is now very, very clear, right? Because if you can have a higher preload, set up the stretching of heart cells, that's going to cause two mechanisms to start changing the way that molecules within those heart cells are working, right? The actin and myosin is actually going to be able to bind more easily to each other, and also the calcium has a bigger effect, kind of freeing up the actin, and at the end of the day you get this larger left ventricular pressure during systole. So really, diastolic preload, or what happens at the end of diastole, which we call preload, is going to have a huge effect on the left ventricular pressure during systole.